Okay, let's get started. In this video, we are going to use the concepts of partial differentiation uh, to prove that given u as a function of x by z and y by z, you should notice that the variables are not the conventional x, y, and z. Here we are taking two variables together and writing as x by z, and there is another variable which is, we have we have taken the composition of two variables y and z. So given that we have got a function as like that, we need to prove that x times the dou u by dou x plus y times dou u by dou y plus z times dou u by dou z is equal to 0. Now, in order to recall, when you're finding out dou by dou x, right, at that time, the variable is x and the constants are y comma z. Both y and z are constants. When you are finding out dou by dou y, at that time the variable is y and the constants are x and z, right? And finally, when you're finding out dou by dou z, the variable is z and like the constants are x and y. Okay, now having said that, let's get down with the solution of the problem. So we first start by creating two artificial variables p and q, right? And let p is equal to the first composite variable, and it's the composition of the variables is x by 7, and the other composition of variables is y by 7. So we'll name that as q. So now why do we do that? Because once you do that, the function u becomes equal to f of p comma q, and we know how to deal with this kind of functions having two variables. So, we can easily define what dou u by dou p is. In this case, p is a variable and q will be the constant. And when we are finding out dou u by dou q, the q is a variable and p is a constant. So we will not explicitly find out what dou u by dou p and dou u by dou q are, but we'll be writing these expressions, and it's completely legal to write them this way. Now, in order to proceed with the problem, we need to since there is a change of variables from the x y z frame to to p and q, so we need to find out how these two sets of variables are related to each other. And hence, we need to find out what dou p by dou x is. And here the z is a constant term, right? So dou p by dou z becomes equal to 1 by z, 1 over z. Okay. Next, dou p by dou y, when you're finding out the partial derivative of p with respect to y, x and z both are constants, right? So x by z is also a constant, and we get 0. Dou p by dou z, in this case, x is a constant, which comes outside the differentiation, and we get negative x upon z square. Okay, having said that, let's move on to q, right? So in q, dou q by dou x is the first differentiation we do, partial differentiation. In this case, y and z both are constants, so the partial derivative of q with respect to x is equal to 0. Okay, next we take the partial derivative of q with respect to y, and in this case 1 by z is the constant, right? So that comes outside, and dou by dou y of y is equal to 1, and we get 1 by z. Finally, remember, we're establishing relation between the old variables x, y, z and the new artificial variables p and q. So we have found out all the combinations. This is the last combination that we need to find out, is the relation defined by the partial derivative of q with respect to z. So in this case, y is a constant which comes outside, and the derivation results in negative y over z square. Okay, now we use the concept of total derivatives, right? In order to find out what dou u by dou x dou u by dou y and dou u by dou z are. So if we look at dou u by dou x, what we do is that we differentiate u with respect to p, right? And but then we need to we actually needed to differentiate u with respect to x. So we multiply this dou u by dou p by dou x, and add the result with the partial derivative of u with respect to q, but times multiplied by the partial derivative of q with respect to x. So basically we are implementing some usage of the chain rule over here, but since the space has got two variables p and q, we use total derivatives to use this formula. Okay, now dou p by dou x is 1 by z, dou q by dou x is 0. We replace those values over here and we get an equation, right? So let's say that this is equation 1, right? And then similarly, dou u by dou q is dou u by dou p multiplied dou p by dou y plus dou u by dou q into dou q by dou y, and dou p by dou y is 0, dou q by dou y is 1 by z, and we get this equation dou u by dou y is equal to 1 by z times dou u by dou q. Let's call this equation number 2, right? So equation 1 is done for x, equation 2 is done for y. Now finally dou u by dou z, again the differentiation of the partial derivative of the given function u with respect to the variable z, right? It's the old original variable. This expression is, this term is there in the LHS of the expression that we need to prove, right? Okay, so again, we are using the new artificial variables. So dou u by dou p into dou p by dou z plus dou u by dou q into dou q by dou z, right? So by using total derivatives, we are writing this expression. But then again, you see that dou p by dou z, we have already found out to be minus x by z square, and dou q by dou z is minus y by z square. So using all these terms, we get the equation number 3 as the expansion of dou u by dou z. Now things are pretty simple from here, right? As you can see that we write down the LHS. Instead of dou u by dou u by dou x, we write 1 by z dou u by dou p. Instead of dou u by dou y, we write 1 by z dou u by dou q. Instead of z dou u by dou z, we write the entire term from the third equation minus x by z square dou u by dou p minus y by z square dou u by dou q. And then when you open the bracket, every term cancel off, and therefore the required statement is being proved. Thank you for watching.